Thanks. I'm extremely happy to be here. So this work is joint with Jan Lukas Igelbrink, who also got the opportunity to be here, and he is a joint student of myself and Matthias Birkner from Mainz, who I understand is also in the audience. So the first part of this talk you can read it in an archive preprint. The second one is very fresh. It's partly what we discussed even here in Montreal in these days. Let me begin with a picture. The Hammond Sheffield urn, they called it power law Polya's urn in a paper which appeared in the PTRF some 9 years ago. And this is the urn. You have balls that find their places at integers, and every integer in the end will be populated by exactly one ball. Right? And as usual, in Polya's urn, say, when you put another ball into the urn, this ball has a parent. Right? That's Polya's urn. You grab a ball, and this is a parent from the one which you take and place back into the urn. And here, this is a spatial flavor, right? Because when you have done the filling of the urn up to time I, say, right, and it started from minus infinity, the parent of this ball number I sits here, and that's a IID copy of a random variable, a random variable with values in the natural numbers. And the assumption is that the tail of this random variable is a power tail. It's going with some slowly varying function times n to the minus alpha, right? And this alpha here, it's the same alpha which appeared in Jason's talk, but it will now be between 0 and 1, right? So it will be a heavy-tailed situation. We won't have even first moments of this random variable. Right, and that's what's said on the first slide. And now we can go on and build the genealogy of this urn, right? And the genealogy is just coalescing renewal processes, because when we have here a J, right, the J grabs its parent, and this one grabs its parent, and when they coalesce, they have found their most recent common ancestor, right? So the genealogy is just a family of coalescing renewal processes running backwards in time, and the source of randomness are just these IID copies of the random variable R, right? Now we have the ancestral lineages. The ancestral lineages are renewal chains, right? They go to the left, and they form what I call here the AIs. These are the chains, but of course, as I said, they are not independent. They are coalescing, right? They form a forest. Right? And the smaller alpha, right? Alpha will be the major parameter here. The smaller alpha, the larger are the jumps of these renewal chains. And well, it turns out, and it will come up why this is the case, alpha equals 1/2 is critical, right? Below alpha equal 1/2, the genealogy forms a forest of infinitely many trees, and above alpha equals 1/2, the genealogy forms almost surely a single tree. Here is a picture how two individuals, these are 0 and 200, how they find their common ancestor, right? Just to give you a flavor, that's alpha equals 3/4. That's the situation where we know eventually they must find their common ancestor, and here they find it somewhere at minus 2000, right? Now, this is a part of the tree, the upper part of the ancestral tree of the individuals from 0, 1 up to 200. I hope one of these beautiful pictures, which Jan Lucas, I mean, he has this double quality, being a very good mathematician and being extremely good in drawing these things. I mean, well, that's self-explaining, because here is the tree top, right? And here you see the ancestral lineages. These little dots are saying, and it's not just a symbolic thing, it's real simulation, right? It's real simulation. These little dots say that you have jumps here, right? And eventually, when a lineage goes vertical, this means you have found a coalescence, right? Okay, that's the upper part of the tree, and that's the lower part of the tree. And here we see around, I don't know, minus 2600. They have found their common ancestor. That's a situation for alpha equals 3/7. So we are above 1/2. And it's no miracle that here we see that those guys, they survive in many ancestral lineages, right? When you go back, and here the upper panel is 100 individuals, the lower panel is 1000 individuals. And so Hammond and Sheffield, they proved by Fourier analysis and by Tauberian arguments, they proved that the dichotomy is given in terms of the renewal function, right? The Qn, the renewal function of this renewal chain. And instead of staring at the well-known definition of the renewal function, we can also say here that the Qn is just the probability that the individual 0 is in the ancestral lineage of the individual n, right? So when we start here from n, the probability that 0 is a direct ancestor of n, that's this Qn. And well, it's just the sum of the Qn squares which decides whether we have a tree or a forest. Benna and Doni, in a recent paper in EJP, they give conditions for what they call the strong renewal theorem, SRT, right? And they give conditions which, together with this ever-standing assumption, are equivalent to a nice power decay of the Qn, because it's not guaranteed that this condition guarantees a nice power decay of the Qn. There are pathological examples where the Qn may, in rare n's, do something strange, right, and not have this power decay. But when I admit I did not really go through this Caravena-Doni paper, but even when one browses it through, one gets the impression that it's a natural assumption to assume this SRT. Right? So we will add for the entire talk this assumption SRT, that the Qn has the asymptotics a constant which is then determined times n to the alpha minus 1 divided by the same slowly varying function. And from SRT, this dichotomy is of course trivial, right? This alpha equals 1/2 criticality. We follow the program of Hammond and Sheffield at the partition of the integers into families with respect to the relation being in the same tree, right? And was done for Hammond and Sheffield only for the case alpha smaller than 1/2. That's the case we will focus on in the first part, after this introduction, so to speak, in the first part of the talk. So P is the partition of the integers, a random partition of the integers, which is given by the mutual relatedness relation. Okay, first part, alpha smaller than 1/2. In that case, the jumps are large, right? And ancestries may miss each other. So we thought of a logo to remember you in which case we are. That's a little picture, cats over cats, even with the source here, right? So we don't want. So this is a case alpha smaller than 1/2, right? Okay, and Hammond and Sheffield, they discovered that the families have interesting fluctuations in the block from 0 to n, right? Because when n becomes larger, old families get into the picture. And of course, also a newcomer has a certain advantage to be drawn again, because generically this probability to be drawn decays within, right? That's the generic thing. And in the tail, it's happening by any means. And so Hammond and Sheffield came up with a coloring of the families at random, right? You have your partition, non-trivial partition, in the case alpha smaller than 1/2, and you color all the partition elements by a coin tossing, by a, say, fair coin tossing. And we can do it even a little bit more general. Let Z be a centered, real valued random variable. When I say coloring, it's a quantitative coloring, right? It's like I color by a real number. And now we have our family Z. They are IID copies of this Z, indexed by partition elements, right? So every partition gets its random color. And what we then do is we sum up the colors, think of plus minus 1, right? In between 0 and n, let n proceed and ask, in the spirit of Hammond and Sheffield, what do we see? And nicely enough, the result of Hammond and Sheffield in this binary coloring case was that this properly renormalized walk, as they call it, this Sn, right? Properly renormalized Sn, namely you speed up time within and you divide through the standard deviation of Sn, which turns out to be n to the minus 1/2 plus alpha. And what comes out is a centered Gaussian process with continuous paths, stationary increments, and this variance, which is just a fractional Brownian motion with Hurst parameter 1/2 plus alpha, right? So, you know, when the Hurst parameter is above 1/2, then you have more regularity than Brownian motion. When the Hurst parameter is 1/2, then it's just Brownian motion, right? So that's the result of Hammond and Sheffield in the case A. And what one has to do is canonical, right? Show the asymptotics of the variance, show that the Sn has this variance asymptotically, then check the asymptotic normality. And interestingly enough, this was the hardest part in the Hammond and Sheffield paper, and prove tightness in path space. Well, that's something I won't concentrate on here in this talk. Maybe can tell you a story in the very end. Now, steps 1 and 2 in Hammond and Sheffield are achieved by, well, they are excellent probabilists, but they did this here by Fourier analysis and, of course, a honorable tool in probability, a martingale central limit theorem, making use of the fact that the coloring of the clans is binary, right? And we had the wonderful opportunity to join a lecture of Alan Hammond in, I think it's already nearly 2 years ago. And that's one of the few blessings of this horrible pandemic, that there were, well, Zoom lectures and we could get into contact with Alan, and he said, yeah, as it happens, I'm giving a course on this paper and don't you want to join? And so, well, we joined and we could even present there our results, and this was very, very nice and very stimulating for us. We work under the assumption SRT and present a series of arguments which constitutes indeed new genealogical proof of their theorem. It's a credo of mine: if you can, then do genealogies first, right? Genealogies first, and then do a coloring if you want. Because sometimes it's good to color. There are the generating functions techniques is also something like this, sort of. But here it's really, we want to know about this tree or this forest. Okay, the renewal function, I wrote it already here. And the first proposition, which was helpful, which we discovered, was that under this strong renewal theorem, also I mean, this nice power law of the strong renewal theorem. I mean, it's a property, right? We could say it's a strong renewal property, which is guaranteed by certain mild assumptions together with this. Then this asymptotics is inherited by the probability that 0 and n are related as n becomes large. Not directly, right? It's not only direct, but you can say the n and the 0 must find the ancestor somewhere else. It's a mini tree, right? With 2 leaves, right? Not just a line. And that's the, if you compare the powers, it's just an additional alpha. Now you have n to the 2 alpha minus 1 as the exponent, and then the variance asymptotics is easy because writing out the Sn, you see that it's the variance of the set times the sum of the probabilities that I and j are related, right? That's different from the classical thing where you have always independent increments. Here it's just this sum ij element of the block of the probabilities that I and j are related. And then I see it should be B, not C, that then you apply proposition 1 and you get the claimed asymptotics of the variance. Let me write it once again here. The variance, I don't know whether this comes in there. The variance of Sn is n to the 2 alpha plus 1, right, times a constant. And you see, you don't reach n square because the alpha is smaller than 1/2, but you may come close to n square. Now, the proof of the asymptotic normality, I won't go into that. I mean, there are the difficulties of and the required ingenuities of seeing how to apply this martingale central limit theorem. This is how Hammond and Sheffield did it, but as we did it, this was looking into other ways of proving asymptotic normality. And then we found a nice source, a nice tool, and this is Stein's method. And so this is even a little bit more general than the Hammond-Sheffield situation. So let me, it's sort of little excursion. Think of a family of random partitions of the block n, which need not be consistent, right? It's not necessarily the Hammond and Sheffield situation, but the same thing is that you color the blocks independently by some centered random variable z, and you form for each n separately, you form the Sn in the very same way as we did it in the Hammond-Sheffield situation, right? So Sn is the sum of the colors of the individuals between 0 and n, where you colored the blocks independently. Now, this is the result which we got on sums of randomly colored sums over randomly colored partitions, and it's in terms of, let me say, coalescence probabilities, right? Because what we do is we grab independent individuals from between 0 and n, right? So this I, j, k, and l, they are independent peaks uniform from this block from 0 to n. And if the triple coalescence probability, right? It's really like, does the ancestry of I, J, and K coalesce, or do they belong to different trees? And that's a probability that they belong to the same tree, right? This triple coalescence probability. If that is little o of the pair coalescence probability to the 3/2, and if the quartet coalescence probability is little o of the pair coalescence probability squared, and if there is a little correlation inequality holding, which I could also tell more about, but then we have the result that the Sn are asymptotically Gaussian. How is this proved? It's a consequence of a proposition which we did not find in the literature, but we extracted from a theorem in these beautiful lecture notes of Charles Stein. And this is it's the same. It's like this. We have the same situation as just described. Then we can even bound the distance between the normal distribution and this scaled SNs in terms of a sum over these pair coalescence indicators and the triplet coalescence indicators. And then one has to check that the Hammond-Sheffield random partition obeys these conditions. And it turns out that we have even a lot of space between what they do and what we would have to check. Because here we get that the triplet coalescence probabilities are more or less of the same order as the square of the pair coalescence probabilities, and the quartet are more or less of the same order as the cubed quartet probabilities. And that the reason for this is that given that I and J, the random ones that I pick, right, given that they find a common ancestor, they do it quickly. Common ancestor is living, given that it's not infinite, right, on the scale n, right? And that's what we also proved. And it's even nicer. Jan Lucas managed to find the real limiting distribution, right? And the limiting distribution is a ratio of a beta over 1 minus beta, which is called a beta prime in the literature, beta prime distribution, and parameters are identified here. So, and that's the intuition for this result to hold. Well, so far this is all in the arXiv, and now case alpha bigger than 1/2. We haven't written anything on that so far, but we have at least one theorem which or a proposition which I also like very much. Well, the logo for this alpha, what would it be? I mean, alpha bigger than 1/2. It's like that the lineages must find each other, right? Eventually, one lineage must jump where another lineage also jumps on, and so we found this logo. It's called cats on cats. Okay, and that's the one and only proposition we have in this part. The other parts are more or less dreamings, but and also invitation, an invitation. So this proposition says that in the case alpha smaller than 1/2, but bigger than 1/2 in this jump on, then the MRCA is almost surely there, right? And its depth is again on the scale n, but very heavy-tailed. It's again a beta prime distribution with other parameters, right? And even it's nice to interpret these parameters. It's like it's like reflecting the alpha on 1/2. So what before was 1/2 minus something is now 1/2 plus something, and that's the thing. Now, again, that's what I said. We know about the depth of a common ancestor of 0 and n. But what about the common ancestor of the entire block? Right? What about this dn tilde, which is the depth of the MRCA of the entire block? And an open question, which sometimes cost us parts of our nights, is there a scale, right, and a limiting variable such that this goes to a limiting distribution on a certain scale? And obviously, this scale must be at least n to the 1 over alpha, because in the generic case where the slowly varying function equals 1, a Poisson limit argument tells you that there are asymptotically so 1 individuals in the block whose parents, whose even parents, right, whose parents are so far away. And of course, that's only then order 1, and they have to find their ancestors. So some logarithms might come in. We have some, it could be that scale, right? But we don't. The ancestral lineages of the bulk of these n to the 1 minus alpha, we call them overjumpers, or if you go to the forward direction, immigrants, right, from the past. This bulk decreases quite quickly. And we have some simulations here, right? It's also a self-explaining picture, I hope, because here between 0 and 100, you have these renewal chains, right? It's the second Markovization of a renewal chain where we look at the remaining lifetime, right? So whenever you are at 0, you get the remaining lifetime, and then you have to work it down, and that's actually the forest or the tree, right? The upper part of the tree, if you like, and they come down quite quickly, and so here is one count path of the ancestral lineages with alpha 0.82, starting from well, 8 such ancient immigrants, and it comes down quite quickly. And we have even a hydrodynamic prediction for this when you insert into this a continuous mass flow, which is eaten up at the origin, right? And this is reminiscent of, it was Matthias who brought us on this path, because in a forward picture under the slogan of self-blocking immigrants, you have a similar picture where the music plays only at the origin, right? And there you produce mass. But here you lose mass in the past direction whenever you have a coalescence, right? So this is hopefully a part which is governed by some hydrodynamics, by some law of large numbers picture, and then some extreme value theory for the loners at the end. Now, an enrichment of the model would be to not look at the renewal chains, but find a process which has these renewal lengths as its excursion lengths. Right? It's just a nice enrichment of the model. This would give rise to random walks on the integers, immigrating at the origin at each point, and coalescing only at concurrent visits of the origin. Now think of ordinary random walk on the integers, right? And let ordinary random walkers immigrate at each time point at the origin and let them move. And whenever two of them come together at the origin, they coalesce. So it's local coalescence of ordinary random walks. Eventually, this will be a tree, right? Because two-dimensional ordinary random walk is recurrent. And we had Bessel random walks today already, and in Ofa's talk. And here they are again in a discrete version. Alexander, 2011, came up with this Markov chain on the positive integers. You see the Bessel drift. And the excursion lengths from 0 of this walk or Markov chain is exactly, has this power tail, has precisely this power tail, right? But this is just, and so we would have another question in terms of Bessel random walks, right? Let Bessel random walks immigrate at the even times so that we don't have a periodicity, right? And ask how long does it take that a block of n immigrants comes down to 1 when we have coalescence only at the origin, right? I'm so happy to see Ted here in the audience, because that reminds me of a wonderful problem on the lonely branches, also in the forward direction. And then we modified it. Matthias was doing his thesis, and we modified it to the local branches. And here we have a backward thing, which is vaguely reminiscent of these things. Now let's revert to the bare bones of the coalescing renewal chains, not Bessel random walks, but coalescing renewal chains. So far, we looked at the backward thing, right? We had these immigrants, and we asked, how long does it take until they come down to 1? But now let's do a cut, because actually that's also related to the seed bank story, right? Here it's coming from the seed bank philosophy, and Adrian, for instance, González Casanova, he's eager to see something like a fractional Wright-Fisher diffusion, right? Something like this. And we are far away from this, but we can, of course, play like this. We can say, cut, forget about what was in the past, like in the Wright-Fisher, in the classical Wright-Fisher, which we saw this morning. I mean, everybody in the Wright-Fisher is related from the past, right? But still we say at time 0, everybody is new, maybe, right? In the Fleming-Vio situation. And we might then come, sorry, yes, I will. And then we can do the post-0 relatives and just say that the immigrants are all new. That has parallels to antiferences to Hoppe's urn and to the Chinese restaurant, of course. And here is a picture of the colors that come up when we have an infinitely many allele situation. Everybody is one's own type concerning the immigrants. That's other pictures here. And in contrast to the alpha smaller than 1/2 case, here we have a significant size biasing effect because we have macroscopic components, right? It's macroscopic components that fight against each other in polar manner, right? They concur in a polar manner. And I say here, these big families compete in a polar-like fashion until they are dwarfed by new families, which then eventually also may become asymptotic. And here are some, here are 3 scales. One is the ordinary scale when we do n versus Sn over n. One is we speed up time, and the second one is, and the third one is we also enlarge the space. And that would be one of these streams, which we even discussed yesterday at the Mont Royal. There could be 3 timescales at least. The original one, where we have something like a metastable situation, a polya thing, and then a power scale, where we see flaming up of old ancestral material and the appearance of new families. And finally, an exponential time scale where everything is renewed and we see global takeovers of new families. Well, that's all. Thanks for your attention, and thanks to the organizers and to the CRM for making this possible.
Okay, it's time maybe for 1 or 2 questions.
Yeah, thanks very much, Anton. So you mentioned already that there is maybe some kind of duality between alpha less than 1/2 and alpha greater 1/2. So I'm wondering whether it's like similar to the duality in Erdős-Rényi in the following sense, that if you take alpha greater than 1/2 and then look at the time scale large constant times n, then I guess most ancestral lineages have, well, starting from most people have coalesced. And now if you look at those who have not coalesced, do they behave like the model with alpha less than 1/2?
I see. So I was not aware of this beautiful thing. I mean, you have Erdős-Rényi, where you have also these power tails.
No, well, in Erdős-Rényi, if you look at the supercritical phase, you look at everything that is not in the giant component. Right. This looks like subcritical Erdős-Rényi, right?
That's
so here
that
I kind of
know. Yes.
Okay. So here I'm just making a very stupid analogy, and I haven't thought about it at all, right?
Yeah,
it's just that I'm looking like this giant component, which is composed of the ancestral lineages that have coalesced, and most of them have coalesced. And now I look at the complement at the other ones. Do they behave like the model with a dual parameter, right?
Yeah, we did not look into that so far, but it's very challenging. Yes.
If not, let's thank the speaker of today again. Let me remind you that there is some coffee and cake in the break room.